Thank you to the organisers for giving me the opportunity to speak here. So, all of you will have noticed that there's been a lot of interest in this model of Sashdev, Ye, and Kitaev over the last year or so. And one of the reasons is that SYK is a solvable model which has features which are very relevant to black hole physics. In particular, it has maximally chaotic behavior. And I'm going to review for you during the talk what SYK is and why it has these features. So, as somebody said in the talk yesterday, you don't get much for free in life. So this is a case where, from the field theory side, we can extract the behavior of black hole physics. But there's a problem in that the dual gravitational description is not so straightforward. And in particular, following the work of Modestana and Stanford last year, it's become clear that the holographic dual is not just an Einstein gravity theory. It's not just Einstein gravity with matter. It should have something else in there too. But nonetheless, 2D dilaton gravity seems to capture many features of SYK. And the main purpose of this talk is really to improve our understanding of why this is the case, building on the work of Modestana, Stanford, and also the Modestana Stanford Yang paper, using generalized conformal structure. So this talk is very much related to, but complementary to, the work of SYK and Papadimitriou, which appeared last year. And it's based on work in progress. So this is a topic where I'm aware that some section of the audience will already be experts, and you can all go to sleep, have a sleep for half of this talk. But at the same time, many of you probably haven't been following it. So I'm going to spend the first half of the talk really reviewing the background story before I go on to tell you what I've been doing with this. And I should say this is work in progress. So let me start with a review of the SYK model, which we haven't heard about so far this week. So this is a model for Majorana fermions in one dimension. So one has, basic kinetic term, and then you have a quartic interaction. And for future reference, it's useful to note that the Hamiltonian is just given in terms of this quartic interaction. Now, the feature which is unusual from the perspective of a high-energy physicist is that the couplings here are taken randomly from a Gaussian distribution. So this is something which is much more familiar in the condensed matter community, but is not something that we tend to think about so often. So the couplings are randomly taken, they have zero mean, and there's a characteristic width of the distribution, which is given in terms of a dimensional parameter j, and then this is a large n model. I should say that this index here, this n is taken to be large, and it scales as n to the 3/2. Now, there are many variants of this model which have been considered over the last year or so. So in particular, instead of having 4 interacting fermions, you can have Q interacting fermions, and that was the case discussed in some detail by Modestana and Stanford. There are supersymmetric versions of this model. There are variants on the coupling. Many of these have been written down. Witten in particular had a nice paper last year. Many other references, which I assure you will be there in the paper that comes out of this, but it's a little bit to the side of this talk. So I'm interested in this talk really in this original model, which has 4 interacting fermions. When one goes to solve this model, which was done by Sashdev, Ye, and then other collaborators later on, you find that there's a bilocal field which becomes classical in the large n limit, and you can think of this really in terms of the average fermion two-point function. And what was noticed is that there seems to be an emergent symmetry, emergent conformal symmetry in the infrared of this theory. And so in particular, if you look at this bilocal field, if you look at the behavior at large distances in the infrared, then this is scaling inversely with the separation, and it scales with an exponent which is related to the number of fermions that you have interacting in the theory. Now, this is theory in one dimensions, so one can think of the effects of reparameterizations, and in particular, as is well known, if you do this kind of reparameterization, you can obtain the finite temperature two-point function. So just directly from this, you can obtain the finite temperature two-point function as well. So up to this point, all I've observed really is that there seems to be an emergent conformal symmetry, which is kind of nice, but is not why people are so excited about this model. So another particularly interesting, No, this is when I say one dimensions, I really mean one dimension. So one space-time dimension, one time dimension. Yeah. So this is scaling. This is scaling. You know, this is the separation in a time direction. Yeah. I'll connect to 2 dimensions a little bit later on. Okay, so another feature which is something which Sashdev has been very excited about for many years in the context of relating to black holes and holography is the entropy in this model. Because this model is something which has an entropy which scales with n even at 0 temperature. And it also scales linearly with the temperature at finite temperature. So beta is the inverse temperature, of course, it scales linearly with this. And so you can write the partition function in terms of the ground state energy, this 0 temperature entropy, and a specific heat, and all of these quantities scale with n. And as was discussed in some detail in previous literature, and then rather elegantly by Montesano and Stanford, you can extract the behavior of the specific heat by thinking about reparameterizations in this model. So again, what Sashdev has been saying for a long time is that this model seems to be relevant to capturing features of AdS2 black holes where one has finite entropy at 0 temperature. So AdS2 cross S2 type black holes in string theory. Which curly J? No, this is fixed. This is fixed. Yes, we'll come to that. Actually, we'll completely come to that. Okay, now so the thing which was, in a sense, was pointed out, I guess, in particular by Kitaev, and got people, again, more excited about this model, is the chaotic behavior that's captured in this model. So over the last couple of years, there's been a lot of discussion about how chaos can be captured by computing appropriately time-ordered 4-point functions. So in particular, this was discussed by Montesano, Schenker, and Stanford. So in the context of this model, we're thinking about some 4-point function of the fermions appropriately averaged over I and j. Now we're working in a larger model, so we have a natural 1 over n expansion. The leading contribution is always going to be the disconnected component, which is not doing anything interesting for us. Then we have the first connected component, which we have an underlying symmetry, an underlying conformal symmetry in this theory in the infrared. And the interesting part of this component of this function is thus expressible in terms of a function of a singular cross ratio. And it's really this that one wants to analyze to see what is going on. So more specifically, as was discussed in the chaos and the butterfly work of Montesano, Schenker, and Stanford, if you're trying to look for chaotic behavior, the required correlator you need to look at is a particular out-of-time correlator, where you basically take the fermions and you separate them by a quarter of the thermal circle. And if you're interested in knowing more about, I will refer you back to their papers. It's not particularly relevant for this talk, so I won't explain it further here. So if one looks at this, behavior of this out-of-time correlator in this model, and you look at the behavior of this term here, you see that it's actually growing exponentially in time with a Lyapunov exponent, which is 2 pi over beta, 2 pi times the temperature, which is in agreement with the behavior found in black holes in Einstein gravity, and saturates the proposed bound on chaos that they had in their paper. So this is a model, a solvable model. I haven't gone into the details of how people actually solve it, but this is a solvable model which displays finite entropy at 0 temperature and displays maximally chaotic behavior. Yes, yeah. Okay, now, as well as this contribution which grows in time, and thus, is responsible for the chaotic behavior, there are, of course, finite contributions to the 4-point function, and these were also discussed by Montesano and Stanford. And as they pointed out, these contributions contain informations about operators that arise in the OPE of this bilocal field. Observed is that these operators form a tower of states with approximately integer spacing, And that would suggest that the putative bulk dual should, of course, have correspondingly fields with masses corresponding to those dimensions in any AdS3 dictionary, and thus that the dual could not be didn't look like it would just be Einstein gravity in 2 dimensions in some way. It would seem to have something else in it as well. And I'll come back to this a little bit later. So that's a sort of lightning review of the SYK models, the features that I will need as I go on. Now I want to talk to you a bit about generalized conformal structure. So, as was well known to everyone in the room, if you have a conformally invariant theory and you have a scalar operator of a particular scaling dimension, then the 2-point function of that operator has this characteristic behavior of 1 over x to the 2 delta. And then there's some normalization here, which you could think of as a function of dimensionless couplings, and parameters. Of course, you could absorb this into your definition of your operator and just normalize your operators to be 1. At the same time, just because you compute a 2-point function to have this behavior in some particular limit of couplings, it doesn't necessarily imply underlying conformal invariance. So many condensed matter theorists, find some correlation function of this behavior in some particular limit, and they say, well, we've got conformal invariance. But this is not true. So there are many caveats, but the particular caveat which is relevant for this talk is the following. Suppose we have a theory in which our conformal invariance, so it's a relativistic theory, in which conformal invariance has been broken by a source for a scalar operator of dimension delta phi. So if we didn't have this source, we would have some Ward identity, which would be that the trace of the stress energy tensor is 0 up to some conformal anomaly. In a theory in which we switched on a source for a scalar operator and done nothing else, and this identity is still respected at the quantum level, then we have a relation instead that the trace of the stress energy tensor picks up an extra contribution which is related to the source for the operator and the expectation value of the operator. And correspondingly, there are diffeomorphism anomalies which say that the stress tensor is no longer conserved. Again, it picks up this extra contribution. So this is, just basic quantum field theory, that this is what would happen. Of course, the thing that's very non-trivial here is that this structure survives at the full quantum level to all quantum corrections. Now, in such a theory, it's clearly not conformally invariant, but it is symmetric under scaling transformations, provided that you also transform the coupling. So in particular, the coupling that appears here, if we allow that to transform as well, so when we do a Weyl transformation, we don't just scale the metric and other background fields, but we also scale this coupling, we will have a symmetry. But of course, this coupling, this source, is something that I just hand to you. So a priori, you can't say that actually, you're allowed to scale it. It's something that's it's handed to you. So this is not really a true symmetry of the theory. It's something that people called a generalized conformal structure. And this generalized conformal structure is captured by the Ward identities here. And if this structure is preserved at the full quantum level, this will clearly imply for us a whole tower of relations on correlation functions. So in particular, it will relate the correlators of 2-point functions of the stress tensor to a 2-point function of the stress tensor with its operator, and so on, by functional differentiating. So it will be a very powerful symmetry. Now, in this theory, the source is dimension full, and so the dimensionless coupling that one can form will be dimensionless coupling at some position at some scale x. And you form it just by looking at the scaling behavior of our source. You form it in this way with an appropriate power of the scale. And in this theory, if you take another operator, so not the operator which is has had a source switched on, but if you just look at another scalar operator of dimension delta, then it would still be true if this has definite scaling dimension, that we have a characteristic behavior for the 2-point function which has a scaling. But we have a function here which now depends on this dimensionless coupling, this effective coupling, in which we have x dependence hidden in it. And then it would depend on other parameters in the theory. So if it's a large n theory, larger n gauge group, it would depend on n and so on. So any function of the dimensionless quantities would be consistent with a conformal structure. I should say this was discussed in a paper with my student in Costas from 2008. So in particular, it happens in many cases in such a theory that this function can actually be expressed as a power series in the effective coupling. And then in certain limits, it can happen that this becomes either constant or it scales with x. So in a generic situation, you would have some series expansion here as powers of x, but in particular limits, you would actually have this would become either a constant or it would scale with x. And so you would seem to have something which indeed just, the correlator just scales as a power law. So the moral of the story here is that just because you calculate something and it scales with a power law, it doesn't mean itself that the theory is conformally invariant. So this may sound to you a very contrived setup, but actually, yes, I think I will address this in a couple of slides, so I'll come back. Yes. Okay. So this may sound a rather contrived situation, but actually it's one that you all know. So one particular example of where this structure arises is maximally supersymmetric Yang-Mills theories in d dimensions. So in 4 dimensions, of course, this is conformally invariant, but outside 4 dimensions, it is not conformally invariant. So if I just write down the bosonic terms in the action, you have the trace f squared, and then you have your scalar fields, you have your interaction between your scalar fields and the appropriate fermion terms to supersymmetrize it. And then the scalar operator that arises here, it's basically just trace f squared with appropriate supersymmetrization. Now in this case, this generalized conformal structure, these ward identities that I wrote down, are respected at the quantum level due to supersymmetry. So you've got maximal supersymmetry, and this respects these identities at the quantum level. And you can show this both perturbatively and in holographic realizations. And so in perturbative realizations, you can do a 2-loop calculation to find the 2-point function of this operator that I wrote here, and see that it scales basically as 1 over x to the 8 and g to the 4. This is just coming from the fact it's a 2-loop calculation. And you can calculate the same correlator from holography in the opposite limit, so effectively the large Toft limit, and you get a different scaling. And so in both cases, the limit for the correlator scales as a power of 1 over x. Remember, hidden here are basically powers of x. In both cases, you get a power of x, but in the 2 limits, the powers are actually different. And of course, by just rescaling the operator itself, by absorbing factors of the source into the operator, you can write both limits in this form with different powers of alpha. And I think coming to Costas's question, yes, indeed, this is a theory in which one is driving a flow. So you've got a flow which is driven by a dimensionally running coupling, and this indeed means it can be relevant and irrelevant, and it means that you will often need an alternative description. This description will break down as you go deep into the infrared, deep into the UV. In the context of maximally supersymmetric Yang-Mills theories, which are of course related to dp branes with p not equal to 3, this was discussed in the original paper of SYK et al., which did holography. But nonetheless, this generalized conformal structure governs the dynamics over a wide range of energy scales. So for many questions, that alternative description will not actually play a role. This will be the governing description. Okay, so now this seems like a sort of sudden jump of topics. What does this have to do with SYK? Well, the point is that SYK itself, the model I wrote down at the beginning, it clearly also has generalized conformal structure. So associated with each of these quartic couplings is a 4-fermion operator. And I can write down a dilatation ward identity which says that the Hamiltonian is just the sum of these, some of these operators with these couplings. So it's precisely the same kind of identity as I just wrote down. The diffeomorphism identity is also, talks about the time derivative of the Hamiltonian, time derivative of the couplings. And let's note for future use that when the couplings are actually time independent, the Hamiltonian in this model is conserved. So this is a case where classically this operator would have dimension 2, so it would be marginal in 2 dimensions and irrelevant in 1 dimension. Okay, so whilst we we have a generalized conformal structure, we expect something else to happen in the deep ultraviolet, well, not deep, in very high energies. This is an irrelevant coupling. Okay, so the first observation is that this model really has a generalized conformal structure, with the deforming operators being these 4 fermion operators, and these couplings, each of these couplings corresponds to a source for these operators. Okay. Now let's discuss how you go and holographically realize generalized conformal structure. So I've noticed that SYK, the classical model, the UV features of this model, seem to have generalized conformal structure. How do I realize generalized conformal structure holographically? So the simplest case I had, where I had just one deforming operator, is realized by gravity with a scalar field. So in particular, if you're trying to realize a d-dimensional theory, you as usual use a d+1 dimensional bulk, and you write down basically an Einstein dilaton model of this form with various coefficients, gamma, beta, and c. And you can always choose your coefficients to give solutions which are basically AdS for the metric and a running coupling which goes along with it. And again, in our paper in 2008, we told you the relations between the constants that you needed to get these solutions. And once you engineer this, you automatically engineer the required Ward identities for the dual field theory, because the stress-energy tensor pulled out of the metric and the operator dual to our field, it automatically satisfies the Ward identity with the right structure. And we would automatically get appropriate conformal anomalies and so on for these Ward identities. Now, it's perhaps not so well known that all of these theories can actually be viewed as a formal dimensional reduction from an anti-de Sitter theory in 2 sigma plus 1 dimensions. So we reduce the theory over a torus of dimension -2 alpha gamma. So these were the parameters that appear here. And if we reduce, our 2 sigma plus 1 dimensional theory over such a torus to d plus 1 dimensions, we take our AdS theory and it comes down to a dilaton gravity theory. Now, in some special cases, this is a positive integer. So in particular, there are cases where we know from string theory, so M5 branes, related to AdS7 gravity, reduced to D4 branes, we know that we would just reduce over a circle. So there are special cases where this is just 1. But the structure actually persists and is useful even for non-integer values. This seems to, capture the physics of the situation. Now, a very special case of the above discussions is the following. So if you take anti-de Sitter and you just reduce over a circle, you actually generate a model in which the kinetic terms for the scalar field vanish. You get a trivial cosmological constant, and then you get a dilaton coupling. And it's trivial here to just include a Kaluza-Klein gauge field as well. This was done in a paper with Blaise Goutereau and Smolich sisters a few years ago. So we take an AdS theory in d+2 dimensions. We reduce over a circle, the usual Kaluza-Klein way. This is the gauge field. This is the breathing mode of the circle direction. And when you do this reduction, you actually get, you see here, so it's just a dilaton coupling, and then we have, there's no kinetic term for the dilaton, so you can actually just rescale the factor of gamma to 1 if you wish, and then we get the coupling of the dilaton to the Kaluza-Klein gauge field. Now, let's think about doing this for AdS3 gravity. So if we reduce AdS3 on this circle in this way, this will reduce down to an AdS2 model. So it will reduce to AdS2 dilaton gravity with a gauge field. So let's think about what happens to the Ward identities of the theory when we actually do this, and the operators of the theory. So in AdS3 gravity, pure AdS3 gravity, the only operator that you're keeping from the dual field theory is just the stress tensor of the dual field theory. And we know the dual stress tensor, the stress tensor of a 2D CFT satisfies the famous trace anomaly relation. This is just the central charge. And of course, it satisfies the conservation relation. Now, when you reduce over a circle, what should you do? Well, you should take your operator, your upstairs operator, and decompose it into Fourier modes, right? So that's what you do. So we're going to reduce over a circle whose direction is y, and we're going to decompose our upstairs operators into Fourier modes. And in particular, we will denote the zero mode components as, this component we'll call the Hamiltonian, this we'll call the scalar operator, and this we will call J. So inherited from these upstairs ward identities, we get a tower of identities between our operators in lower dimensions. So when we do the reduction of the two-dimensional field theory to one dimensions, the AdS3 reduction to AdS2 dilaton gravity, we will keep the zero mode components of the ward identity, and then we get a relationship between the Hamiltonian minus the operator is just an anomaly, and then we get these conservation relations for the operators as well. I'm sorry, that should be curly h there. Which is very similar, but not quite identical to the SYK dilatation identity. So we already said at the beginning that in the SYK model, the Hamiltonian was basically equal to the sum of these operators. And I put the curly twiddle here to denote that there could be quantum anomalies here. Now, when we do this reduction, we can also just reduce the correlation functions of our upstairs operators to get the correlation functions of the downstairs operators. So again, it's well known that in two-dimensional CFT, you can get the two-point functions just from integrating the ward identities. So we're used to writing the two-point functions of the stress energy tensor in a two-dimensional CFT in terms of holomorphic, anti-holomorphic language. But here I'm reducing on a space-like circle, so I have to first write things in Cartesian coordinates, which I'm sure is in the literature somewhere, but actually in a paper a few years ago we wrote this down explicitly because we needed to do a deformation in the time direction, so we wrote everything in Cartesian coordinates. So for example, if you take the two-point function of the TT components of the stress tensor, in terms of the time and the spatial y coordinates, this is how it looks, and there are corresponding expressions for the other two-point functions. And I should say I've suppressed local contact terms here and everywhere that follows. So following the procedure I said before, writing everything in Fourier modes and decomposing on a circle, you can show that the operators, the zero mode components of the Fourier decomposition, these two-point functions actually just vanish. So these terms all combine, and actually they just vanish up to contact local terms. So it's a peculiar set of operators that we get here because their two-point functions vanish up to just contact terms. On the other hand, if you look at the higher Fourier modes of the 2D stress tensor, these essentially have exponentially decaying correlators, so they're behaving like something that is massive. And these results, I should say, follow trivially from the reduced ward identities, from just decomposing the ward identities in Fourier modes. The triviality of the zero mode correlators is just a consequence of the fact that these operators were actually conserved. Okay, so the dilaton, what we're saying is that the dilaton gravity theory, it captures information about operators, dual operators in whatever the 1D dual theory actually is, but these operators have trivial correlation functions. On the other hand, they're not entirely trivial because they can have non-trivial one-point functions. So in particular, if you take the BTZ black hole and reduce it on a circle to 2 dimensions, you get this two-dimensional metric, this gauge field, and this coupling. And if you just read off from the standard holographic dictionary, what is the expectation value of the Hamiltonian, the scalar operator, and this as J operator, then this is given in terms of the positions of the horizons R plus and R minus of the black hole. And the normalization constant here is proportional to the central charge of the theory. And if you go on with this, you can see that actually this will indeed capture exactly the thermodynamics of SYK. Or another way of saying it is that the thermodynamics of SYK is really controlled by the fact that there's a generalized conformal structure. And this was discussed in some detail by SYK and Papadimitriou last year. So these operators are not entirely trivial, even though their two-point functions vanish. Okay, so let's now turn to the dual of SYK itself. So we've seen that the dilaton gravity seems to get some things right. It would get the thermodynamics right, but there's clearly some things that it's missing. So in particular, one of the things I told you at the beginning was that SYK has an operator which has a two-point function with scaling behavior. And this was clearly not there in the dilaton gravity model, because I just told you that their correlators were actually just vanishing, right? So they're not there in the model. So how are we going to realize that? Well, one way to see where this comes from is to, again, think of the upstairs picture in terms of AdS3. So you put a test scalar in AdS3, that's dual to a two-dimensional CFT operator, and the usual relationship between the mass and the dimension of the operator. And again, we will actually use a mixed representation of the operator, in other words, just decompose this upstairs operator in terms of Fourier modes, and see what happens when we reduce both sides on the circle. So you reduce AdS3 on a circle, you reduce your two-dimensional CFT on a circle, what happens? Well, when you do this decomposition, you see that the zero mode component does not have exponential decay, so this term is just a constant, it just has power law behavior. But then all the other higher modes, the higher Fourier modes, have exponential decay. Yeah. So one place to get, so if we're looking for an operator which has power law behavior, we can see that it would come from keeping the zero mode of a scalar, just a test probe scalar in AdS3, and reducing on the circle. So if we actually do that, we take a massive scalar field, we just reduce on a circle, we keep the Fourier, well, this is written more generally, we'll decompose it into Fourier modes and write things, just write the reduced two-dimensional action. We get this form. And we should note that the mass here, in the case of the non-zero modes, it depends explicitly on the dilaton factor, so it's actually varying with the effective mass is clearly varying with the position, because the scalar is varying with the position. But the zero mode, it just has a fixed mass. But actually, here, the zero mode would not be minimally coupled in Einstein frames. So here we write this in terms of a dual frame metric where we have this coupling, but the zero mode would not be minimally coupled in Einstein frame. So you can reduce the standard. You can use the standard AdS-CFT relations to reproduce the scaling behavior for the two-point function for this zero mode, and that would indeed give you the behavior of the SYK operator. And in the case where we're considering the dimension to be extremely large, we can also get this geometrically. So you can consider basically a geodesic. So here's Euclidean AdS2. The boundary here is now Euclidean time. We have 2 points separated in time, so the two-point function is effectively calculated just by considering a geodesic in the dual frame metric. So this gives us the origin of what we would need to do to get the SYK operator. On the other hand, to match the dilatation ward identity, the bulk dual should have a scalar for every scalar coupling. So there are multiple couplings in the SYK ward identity, and we would need a scalar for every such coupling. So the natural thing to do to try and holographically realize SYK would be to have basically a large number, n, of order n scalar fields for every coupling. And so if you write down this action, you can still get AdS2 solutions with scaling behavior for the scalars. And now the ward identities for the dual operators, we basically just have a whole series of scalars here. So every, each of these alpha A's matches each of those couplings that I had at the beginning. And we can match the SYK story provided we choose these sources or these powers here to be taken from a random Gaussian distribution. Actually, the way, just to present it slightly simpler, the case with no kinetic terms for the scalars involves a constraint on these couplings, but I could just relax that constraint by including more general kinetic terms over here. So the claim here is that if you really want to realize the dual of SYK, you have to do something pretty peculiar from gravity standards, because you have to have, to capture the Hamiltonian, you have a two-dimensional metric. But to capture the n different couplings, for every different coupling, you need a scalar field. So you need a large number of scalar fields in the bulk. But you can do it. You can cook up a model that actually matches the structure of SYK. Now, the other thing I said about SYK is that the 4-point calculation suggests that there's a tower of low dimension operators. These are clearly different from the Kaluza-Klein towers that I got from a circle reduction of a CFT, because I showed you that those have exponential decay. They don't have scaling behavior, they have exponential decay. I should say, however, that there are other ways to get dilaton gravity from reductions of supergravity on spheres, where you do have a Kaluza-Klein tower of integer-spaced operators, and that might be one way to do it. But let me just stick with the AdS3 case for a moment. So, since the 4-point function has an infinite tower of spaced modes, for every operator which we found in the OPE, we need a dual bulk field. And we know, just from the usual rules of holography, that this implies that there must be a coupling between this dual bulk field and the scalar field that I already introduced to represent the bilocal operator in SYK. So the action that I'm sort of bootstrapping up has got increasingly complicated, right? Because I already said back here that I needed to introduce, for every coupling, I needed a scalar field. So I've got n scalar fields. Now, these are not going to be the SYK bilocal operator. That I had to introduce by, this field phi here. And now I know that this bulk field corresponding to that bilocal operator, this has couplings with an infinite tower of other operators of different spacing, and so I know that we have to have these couplings must be there as well. So just on principle, to get the features of SYK, you could not in principle expect to be able to do this with a consistent truncation to a finite number of fields. So I had n scalars from this, I had another number of scalars which are growing with n. We cannot in principle get these features from a consistent truncation. We could not expect to be able to do so. We shouldn't be entirely surprised by this actually, because the finite contributions to the 4-point function are, of course, sensitive to the full tower of states which are exchanged. So this is a Witten diagram. We're trying to calculate a 4-point function. We will have this kind of, exchange here, and we need to, consider the full tower of things that can be exchanged. And even in the best understood case of AdS5 cross S5, you need to take into account the full Kaluza-Klein tower of excitations on the S5. You have to exchange all of them to get the finite contributions to the 4-point functions. So if we're just interested in this dominant term, which is the growth in time, which is controlled by the Lyapunov exponent, we will actually need to look only at the background geometry. So the discussions of Schenker and Modesena and Stanford were based just on the coupling to the background metric. If you're interested in the finite contributions, you will always have to know about the full tower of states. So we should not be surprised that we would be unable to get this without having, in a sense, the full knowledge of the bulk spectrum. Okay, so this is a bit, negative in that I'm saying that if you really wanted to realize the features of SYK holographically, even bootstrapping it up, it would be pretty complicated. You would need a large number of sets of field. So let's turn this question round in the last few minutes. So what we've been using here is really the following. So we have said that for any parent AdS3 theory, you would get a dilaton gravity theory, which by the reduction of CFT2 down on a spatial circle, always gives you a dual one-dimensional theory which has this conformal structure and has many of the features of the SYK model. So what we can do is we can take any of our favorite AdS3 CFT2 correspondences and reduce them on a circle. We can also, I should say, I mean, this is a conference about AdS3. As I said before, there are other ways to reduce supergravity down to get dilaton gravity. There's a whole plethora of things. So let's think about what happens when we do this. So one of the best understood examples of AdS3 CFT2 is, of course, the D1, D5 system. So the D1, D5 system, one way to understand what is going on is in terms of a deformation of a free orbifold CFT2. So at the orbifold point, one can describe this in terms of free bosons and fermions, where these indexes, this index A runs between 1 and 4, this index I runs between 1 over n. And now, to move away from the orbifold point, you need to make a marginal deformation. I haven't written it down explicitly because it involves the full structure of the twisted sectors. but it's known explicitly what the marginal operators are deforming you away from the orbifold point. So this theory, of course, by construction, it is a superconformal field theory. It has conformal symmetry, and beyond that, it also has superconformal symmetry. If you reduce this on a circle, so you reduce these scalars down on a circle, you reduce the fermions down on a circle, and you reduce the marginal deformations down on the circle, by construction, you are going to get something which has the generalized conformal structure, and of course it has supersymmetry, which guarantees that this persists at the quantum level. So if one is interested in exploring a one-dimensional model which has the features to describe dilaton gravity, you're trying to understand whether it would be able to capture the features of a two-dimensional black hole, this looks an extremely good starting point, because this is a model that we understand very well. There are many experts in the room who know extremely well what these operators actually are in terms of the twist sectors of the orbifold, parent orbifold CFT2. So a basic question you can ask is, when you take this kind of model, does this model exhibit chaotic behavior? See, we know that as we go far enough away from the orbifold point, it must do, because we know that it's holographically dual to the AdS black holes. Of course, the question is, how far do you have to go away from the orbifold point? And so can one explore this? And this is the question in progress. Now, this thing here, anyone who follows the Independent newspaper in the UK might know that there's a columnist there who talks about questions to which the answer is no. Is Brexit sensible? Does Donald Trump know what he's doing? Anything which is written in a headline in a newspaper with a question mark, the answer is almost certainly no. So it's quite likely that in this case, I would say that this is a question, does my reduction exhibit chaotic behavior? Probably not, because probably just going, deforming away from the orbifold point is not enough to see maximally chaotic behavior. We're probably not going to get the Lyapunov exponent to saturate the bound. On the other hand, it's probably interesting to explore these models for many other reasons to actually understand this behavior further. And that's the work that's in progress. Okay, so let me summarize here. So what people have been calling over the last year nearly conformal AdS2 is an example of a very well understood story which has been around for a while, which is generalized conformal structure. The dilaton gravity people have been discussing arises not just from AdS3 reduced on a circle, but other supergravity reductions, in particular four-dimensional theories reduced on a sphere. And this gives us a very large class of dual supersymmetric one-dimensional theories which have generalized conformal structure, of which the one that I've given here is just one example. So this is, if one is interested in exploring the relationship between black hole physics, black holes in AdS2 dilaton gravity, and chaotic behavior in one-dimensional theories, this seems like a very natural starting point to actually look at these theories and to try and understand more what are the essential features. I mean, it has been suggested that this Gaussian random behavior is absolutely essential, but it will be interesting to understand this more. So let me stop there.
I guess I just didn't understand. In the SYK model involves an stochastic averaging. So when you introduce these different scalars, what kind of averaging do you do on the gravity side?
So that's what you have to do. This is, in a sense, the very weird feature, right? That you have to do the stochastic averaging of these couplings here. That's what you would be asked to do, which is, of course, a very unusual thing to do in gravity. Yeah.
So you compute the correlators and then you do
no.
I
would actually impose this at the level of the solution. And I can also ask questions. I should have said, actually, I could also, this is going to give me the UV behavior near the boundary. I can also ask questions about whether in the deep infrared, where I'm driven to, whether my solution is stable, whether I'm driven into something else. But that's the claim, that you would actually have to do a stochastic averaging of the background solution itself.
And the dependence of the dilaton on the radial coordinate, is that something that is probed by some correlator in the SYK model, or?
Yes, it would be. It would be, yes. Yeah.
So it is a little bit troublesome, though, that you have n scalars.
Yes.
Okay, because it doesn't
Yes.
look very classical.
But that's exactly my point. That's exactly my
Okay,
point.
okay,
That's
I wanna-
exactly the point, that actually...
It looks good, like worrisome in terms of like.
But
how
that's if you want to realize the defining ward identities of the SYK model, that's what there is
Yeah,
there.
that's what I remember, because in the Maldacena Stanford papers, they were saying this is a string theory. It's not really a classical theory
That's
of
right.
gravity.
That's right, but at least, you know, asymptotically, I mean, as a sort of bootstrapping the effective description near the boundary, this should be allowed. Right now, the is this stable at the quantum level?
Yeah, like
Yeah,
as an effective
probably
field
not.
theory point of view, I would be nervous that you have so many fields.
Absolutely,
scaling. Okay.
absolutely, yes.
Maybe just to clarify that, was it n or n to the power 3 or 4? Because the number of couplings is bigger than n.
That's right. Yeah, I'm not
So
being
it would be a
careful.
larger number.
That's right.
You're talking n, but you meant.
That's right.
n
Yes,
power.
that's right. Yeah. But can I say, I mean, you know, this is of course true, but at the same time, if you want to calculate precisely correlators in AdS5 cross S5, you actually do have a large number of fields, right? That's not entirely true, right? There's consistent truncations to subsectors, but there's not a kind of gap, yeah? But there's a consistent truncation to just to gravity and a small number. But if you want to know just even the finite contributions to the 4-point function of a chiral primary, then you already need that. But I mean, I think my whole point is indeed that this just tells you that it's SYK, and that, you know, that it got some features right because it shared the generalized conformal structure, but actually you really don't expect to be able to do it this way. Yeah.
Maybe just another follow-up question about this large number of extra degrees of freedom which you advocate. Maybe those are actually visible in the so-called tensor model version, because that in the SY case, right, those are random matrices. You have to average over them, but in the tensor version, there are indeed large number of genuine extra degrees.
Yeah.
Probably it's more natural for those.
No, I agree. Yeah.
You said that the model, SYK model, was exactly solvable, and any correlation function can be computed, right?
Well, I don't think I was that precise, because I have to check the literature and say, is it exactly solvable or solvable in the sense that...
Well, but you said that all correlation functions can be computed,
Yeah,
right?
I believe so, yes.
So then I'm a bit confused. If you know all correlation functions of the model, why can't you just reconstruct the dual gravity theory?
Why can't you reconstruct?
Reconstruct the dual gravity
So
theory.
in a sense, that's what I'm doing. That's exactly what I'm doing. I'm bootstrapping it. Exactly. So I'm saying that, you know, in principle, sorry, let me go here. I'm saying that in principle, that's exactly what I'm doing. Yeah? I can actually cook it up to do this.
So
But the question is this a sensible thing to do if we have a large number of degrees of freedom? But, you know, yes, I can try and do that.
Well, in the large n limit, you are supposed to have classical description, no quantum corrections, right? So you would not be dealing with quantum gravity, you would be dealing with classical gravity.
So in the large n limit, you have a classical description in the field theory. So the general rule of thumb is that you're not allowed to have two different classical descriptions of the same physics, right? So this was another rule of thumb that said that probably the gravity was not going to be well described by classical
in the
gravity.
large n limit, in large n limit of the SYK model, it's quantum theory. And it is supposed to be dual to classical gravity theory.
Mm-hmm.
Right? Am I right or not? I'm not an expert in
I think we should discuss afterwards, actually. So that's my...
This is meant as a classical theory, just couplings are to be averaged a little bit.
That's right. So this is just trying to bootstrap the information that you actually have into what would be the bulk action that would reproduce this using the standard rules of holography. And then the next question, as already raised, is this something that would make sense to do if you have a very large number of fields and you don't have gaps? Is this something that you would want to do?